How are we doing the first two? Questions? How are we doing number two? Erythro, OH and Cl on the right with the methyls at top and bottom. How we do? Good. Three. How we do? Mechanism. Alkene protonated. We make a ring. Oxygen has attacked something. If oxygen attacks here, it's a 7-membered ring. We need a hydride shift, 6-membered ring. Cation with methyl and ethyl. Methyl and ethyl. Oxygen attacks cation. We remove the H using something like the bisulfate, or you could use water. How we do, guys? Questions? Okay. Key will be posted upstairs. Resonance handout. Any last questions about the material for test tomorrow? Any other questions about the quiz we just took?
Yes, I have one.
Yes.
So I'm not understanding, and I guess this is me needs to be more practice, but for your visual projection, I got my OH and Cl on the right.
That's correct.
You said it was on the left. I mean, I got it on the left. You got it on the right.
Okay. Let's look at it together. Other questions?
I got mine as 3. I don't know, I just did I figured out my projections wrong. I didn't do it. I can't figure out how you do it anymore.
I recommend turning the alkene first. I'd recommend turning the alkene first. Return the alkene first.
What problem was that for? Number 2.
I turned the alkenes first. There used to be a double bond here before I raised it, right? There's the alkene I just turned. What does the reaction do? Chlorine and OH, it's halohydrin. These are going to be trans. Coronium, water backside attack, yeah. OH is going to be on more substituted carbon.
Do you know which house is going to come down?
No? Plus an enantiomer. Who turned the alkene before you did anything?
I turned it, but I put my I put the ethyl and the methyl coming out versus going back.
Well, you just get the enantiomer.
And that's okay?
Well, you may not get the enantiomer, because if you did that, but you bring it in from the top, other way, you might get the same thing.
I got the enantiomer,
Okay,
but that's acceptable if you put plus enantiomer? So mine was the same. I had my OH and my chlorine on the left,
uh-huh.
which is just the enantiomer of what you have there, correct?
It's just the enantiomer, yes. That would be okay.
Okay.
It would be erythro, though.
It was.
Okay. No other questions about that? All right. Guys, if you have questions, you should raise your hand, shout it out, say, hold up, I got a question. Please do that, okay? Otherwise, I'm heading on. Resonance outline. Pink. Everybody gets a pink sheet. Test tomorrow. Nomenclature. Maybe some multiple choice. What else do we have? We have predicted products, alkene reactions, alkyne reactions. We have stereochemistry, plenty of that. Short answer like quizzes. Mechanisms. Okay, using arrows appropriately to show all electron movement. No spectroscopy. It's the only test you'll ever have with me with no spectroscopy. We did some thermodynamics, kinetics. What else do we have? Any other questions about the tests?
If something is diastereomic selective, can you briefly just explain what that means? I kept...
This reaction we just did,
Mhm.
it only gave erythro. Would you agree?
Yes,
It did not give 3O. What's the relationship between erythro and 3O?
diastereomer.
Yeah. So we say it was diastereoselective. It only gave one diastereon, not the other. Now, was that reaction enantioselective? Did it give one enantiomer but not the other?
No.
No, it gave both. I had to put it up there. I didn't. Plus enantiomer. So it's not enantioselective, but it is diastereoselective.
I'm sorry, I'm a little dense. So what would be an example of something that is diastereomic selective?
That reaction.
No, okay, that isn't, rather.
It is not diastereoselective. Well, I can give you reactions where it's not applicable because there's no diastereo possible. Have we done a reaction that is not? Yes, we have. Yes. We may haven't focused in on one, but something with like a hydride shift and carbocations, you're going to attack either way. You could end up with, let your mechanism dictate it. How did you arrive at the, before we do it in the Fisher, how did we arrive at the chlorine up and the OH down? Mechanism, okay? But what if it was just cations that you attacked? Would you attack them a certain way? Yeah, if it was all just cation chemistry, you could end up with both up, both down. But this could be down, this could be up, or it could be like that. And you would actually get all four. And if you drew them all, you get both erythro and 3O, and you would say it was not diastereoselective. I don't know that we focus in on one. What's the reaction we talked about there, regioselective?
No.
Yes.
Sure it
Well,
was.
no, yeah, it was.
The chlorine, chlorine's really gonna attack them.
The chlorine, well, talking maybe about the water attacking the chloronium. The water only attacks the one side of the chloronium. It does not attack the other. So of the two possible theoretical choices, it only attacks one. It only ends up bonding to one region. That reaction was regioselective, diastereoselective, but it was not enantioselective.
Can we go over number one in the workbook? I think a couple of us are confused.
Thermodynamics.
Number one in the workbook, and I continue to not bring my workbook. Sorry. Number multiple choice, page 48. Is that it? Is the answer C?
It is.
Maybe tertiary cation. Tertiary cation?
But the fastest rate, wouldn't it be the least stable?
See, that's a little apples to oranges. Because you're looking at the startings, and this was already higher. It's an apples and oranges question. I don't like it, but you may see some. If you start here, two start here, they're going to the same place. Which one's going to get there faster?
The
That
least
one.
stable.
But what if they're not going to the same place? And this one's going here, but this one's going here. Which one's going to get there faster?
Bottom.
Well, the bottom one. So you got apples and oranges. You got two different things going on here. And when I showed you this in class, I don't like the question. I don't like it there either. Ultimately, tertiary carbocation is sort of. I should remove that question. But sometimes you see that question in textbooks, and I'm like, I don't like this question because you got two different variables. Yeah?
Got more information as far as discern the answer.
Correct. If you understand why it's a bad question, then you're in good shape. If you're going to the same spot, then we can say, I don't think those cations are going to be the same. I'm pretty sure that's the answer, but the explanation doesn't fit. It's not. Yeah.
Can we do one more, number 34 in the workbook? I've got it worked out here.
Multiple choice.
Yes. The answer is B, but I thought it should be E.
The answer is B is in boy.
Yes, but I thought it should be E.
E is in elephant.
Elephant.
Burning water. E?
I thought it should be E.
E uses poison catalyst.
Exactly, but so does, no, it doesn't. No, yes, it does.
B?
So does B.
Yeah, but it uses it first. And so it takes you to the alkene first, and then you do the halohydrogen. E, you do halohydrogen, well, it's...
But we're trying to get a cis addition of the duroniums, right? So
Cis addition of what?
the D's, the hydrogen.
Syn addition.
Syn addition.
Uh-huh.
But the original, so the baronium, the hydration reaction with the halogen is going to give you a trans addition of the halogen and the OH, correct?
Uh-huh.
So I thought if those are going to be trans, do those first because deuterium? What is it called? Those guys are going to come in cis and force that trans, the oxygen, the OH and the halogen to the same side.
Why would them coming in force a trans product cis?
I don't know. But, I mean, it's the same thing, though. So why on B would...
Draw each step out, and we'll have to look at it after class or something. First off, you just got it wrong in sequencing, because the poison catalyst does nothing with an alkene. You do a poison catalyst, it stops at the alkene. That's a reaction of alkyne to alkene, and it does not go further. Your product is an alkane, so it got reduced further. But poison catalyst does not reduce things further. So there's your main problem. Even if it did, your stereochemistry description seems backwards, because remember you got free rotation. Just because you show things both bolded doesn't mean that the mechanism was that. So maybe the mechanism led to this, but when it was drawn, it was just rotated.
So a poison catalyst will never react with an alkene.
Well, look where we introduced it.
Yeah.
We said alkene to alkane, I put a big X.
Okay.
That means it does not happen. Yes.
Can I grab a pink?
Okay, resonance. New material. Test 3. We spent almost 30 minutes on stuff where this time should be dedicated to test 3. Resonance. Never heard of resonance? Okay, let's cover resonance now. I don't know if we've ever mentioned it before. Maybe? Okay, intro to resonance. Also known as delocalized bonding, or pi bonding. Outline, heading. Sounds like it's important to make it a heading. Neutral conjugated alkenes. First off, stability of conjugated dienes. What's a diene? Got 2 enes. Yeah? Diene. This is a conjugated diene. The double bonds are conjugated. That's a non-conjugated. They are not conjugated. Conjugation refers to p orbitals. P orbitals lined up. The 2 enes are conjugated. That is, if you show the pi bond comes from overlap of 1 electron p orbitals, right? Well, then you got here also 1 electron, 1 electron. There's your 2 pi bonds. But look, these 2 p orbitals are next door. Are they interacting or not? Are these 2 interacting? The answer is certainly yes, they are. That looks like a pi bond. Well, where's the pi bond at here? That's because we're not showing it. Once we have resonance and conjugation, the structures we draw tend to be no longer correct, or no longer fully correct. There's some pi bonding in between carbons 2 and 3 that is not shown by the standard structure. You've got to know that. Yes, p orbitals next door, even though they're here. So what you have here is all 4 are lined up like toy soldiers. They're all said to be conjugated. And it becomes really one system if we take it further.
Is that what makes it more stable?
Yes, yes, because you see why this one's more stable. Yes, non-conjugated. Here's your pi bond. Here's your pi bond. Carbon in between, though, is sp3, no p orbital. So, are these 2 alkenes conjugated with each other? No, the conjugation is disrupted by the lack of a p orbital on the sp3 carbon. Which one's more stable? Yes, conjugated is more stable. Why? Because the interaction with p orbitals is like additional bonding. Additional bonding sounds like a good thing. It is. More bonding between your atoms, the more typically it's going to be more stable. Until we get to some strange things like anti-aromaticity. Okay? How do we know? Where do these numbers come from? Heats of hydrogenation. You hydrogenate this diene. You can add hydrogen to both and get an alkane. Do the same reaction here, you get the same product. But this one gives off more heat. Has a higher heat of hydrogenation. Gives off more heat because it contains more energy. It's less stable. This here is a little bit odd looking, isn't it? Carbon with like 2 double bonds. First off, is that a valid structure? Or is there something super wrong here? How many bonds is the middle carbon making?
4.
4. It's a good structure. What's the hybridization of the middle carbon? SP, yes. SP linear. Yeah. Okay, are those two double bonds conjugated?
Yes.
Well, if you can read.
No.
No. Why not? It's a good structural consideration here. Why are they not conjugated? Okay, here's one. We got carbon, carbon. This is going to be the center carbon, right? Okay, one electron makes pi bond. Center carbon. You said it's sp, so how many p orbitals?
2.
2. Okay. Carbon on the right is going to be the center one. I drew one p orbital. We've got to draw another. How's the other one going to be positioned compared to the first one? Perpendicular. Okay? It's coming straight out. I can't draw it straight out, so I'm going to draw it something more like this, and maybe make it look a little bit bigger just to make it distinguishable. They're the same size. Okay? And this is a, oh, by the way, there is a sigma bond between those over there, yeah? And there's a sigma bond between these. Okay? One electron. Well, what's that? What's this p orbital one electron interacting with? Yeah. One electron, you get pi bond. But these two pi bonds are perpendicular to each other. One is 2p orbitals straight up. Straight up, yeah. That one's straight up. But this guy has 2p orbitals. They're like this. One straight up, making pi bond like that. But the other one is like this. And interacting like that. You got two different planes here. They're not conjugated. They're not lined up. It's like one's here, but the other's like this. And p orbitals have to be fully side-to-side overlap to be bonded. Okay? That's a good structural consideration. Good compound here. It's called accumulated. Those double bonds are called accumulated. Not conjugated. It is a diene, though. There's two alkenes. You don't see this much. Occasionally you see it on exams, because it makes you have to realize the structure there. Benzene. Benzene is a fully conjugated cyclic system. That is, every carbon has a p orbital. Every atom has a p orbital. And they're all lined up. You can have it flat with them all just 6 like this. Okay? And if you have a fully conjugated cyclic system, that equals aromatic. Well, not always. It could be anti-aromatic. Benzene is the granddaddy of all aromatics, all carbon. Benzene is a compound. It's discovered by who? Michael Faraday. Distilled it from shelled oil gas. Okay. The lining up of the p orbitals is a good thing. Showing dipolar resonance structures and predicting major resonance structures. Okay, this is actually a tough place to start. And sometimes I probably may skip this. Let's say some. We'll look at the structure, but we may not draw resonance structures. Mainly the problem is it's not polarized, and so the direction of the electron's movement is unintuitive. That may make sense a little bit later. Okay, we got a conjugated diene. All right? Same as above, right? Except we just got one more carbon, but that doesn't have a p orbital. There's no p orbital here. common question we could ask here, we did back at the beginning of test 1. How many pi electrons in that conjugated diene? Or this one, the answer is the same. How many pi electrons here? 4. One electron makes pi bond, one electron makes pi bond. 4, right? You got to know your structure, basic organic structure. 4 pi electrons.
So they're just delocalized like across all bonds simultaneously?
If you want to discuss that a little bit more, boom, boom, boom. We got p orbital. It's the same as above, yeah? One electron, one electron, one electron, one electron. Okay? Interacting here, but it's all interacting here. And basically what you got electrons all through here. It becomes one system. And then we get on between, we still have atomic orbitals. That's a p atomic orbital. You're pushing your way towards molecular orbital theory. Okay? That's the same as we drew above. Dipolar resonance structures. Let's go ahead and do it. I may quickly move on below because it's just, we can polarize. Pi bonds are very polarizable. That is, okay, boom, or maybe you can pull. Who usually gets to win? Well, more electronegative. If you're oxygen, you're going to pull the pi bond more towards you. Okay, what's more electronegative, carbon or carbon? You see, there's no polarity here, so the way the electron's moving is not intuitive. For example, what if I just move these electrons here? Pi bond. What if someone grabs my hand and just moves the electrons here? Now I'm going to be a lone pair. Boom, 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 boom. Here and plus there. We could go backwards. That is, I could move the electrons back in here and remake the pi bond and come back here. This is a resonance structure. Because what's the definition of resonance structure? Just an alternative placement of pi electrons. You do not move any atoms. Are any atoms moving going from here to here? No. The only thing moved is pi electrons. That's resonance. Now, once we get here, could we show another resonance structure? What would it be?
You could move one pair to the end of the other.
Oh, you want to do it this way?
No.
You could, and that would be a resonance structure. But then you would have 4 charges.
It would be a very
So the left.
Then you assess each structure, yeah. Instead, let's sort of, what if on day 1 we had a cation? Something over here has to share. Okay, we're going to start new windshield wiper. What if we take these electrons, instead of having them positioned over here, move them over here? Windshield wiper. That would be boom, 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 boom. What's now on this card that we need to show? It lost a bond, positive. We didn't do anything here. That's still negative. What's the charge of this carbon? How do you know it's neutral? You just made another bond. You got to keep track of your H's. I mean, how many H's here? Same number is there. 1 H. There's 1 H there. So if it's 1 H, that carbon has 4 bonds. Got to keep track of H's. These are resonance structures, because isn't that just a same connectivity, just a different position of electrons? But usually when we start drawing resonance structures, we do it systematically, one step at a time, and we move electrons a certain way. The true structure is in between all of your resonance structures. That doesn't mean it has to be right in between. You assess each resonance structure and say, okay, which one is the best? If I had to show this compound with the electrons arranged the best, This is just three. There may be more resonance structures. But of the three, which one's best? This one here. That's the best. Why?
Bond.
No charges. Creation of charges is usually bad. Because you're selling these charges to separate, and now they're sitting there with this charge energy. This is best. So we say that the hybrid, what is the hybrid going to look like? The hybrid is where you show sort of the blend. Now this gets a little difficult because whenever I show blends, I just show them kind of half and half. That is right in between. But look at this. Your true structure is a blend of everything. Between carbon 1 and 2 is a double bond. But here's a single. What's halfway between double and single? 1.5. So that's supposed to illustrate sort of 1.5 bonds. How about between 2 and 3? Single, single, but double. So it has some double bond character. What's in between single and double? 1.5. Now you may say, let me ask you, is there more single bond character here or double bond character?
Single.
Yeah, you got 2 singles and 1 double. But again, that's hard to differentiate here, so I'm just showing it 1.5. How about on the end? Double, double, single. So it's not a full double, it's got some single bond character. This starts to be more what the compound looks like. And what I drew before I erased it, I show all the p orbitals, they're all interacting, the electrons are all through there, here. Charge. Oh, this gets difficult because we could have polarized it the other way. And I could have drawn these same things but with charges on the right side. And they really would cancel out. We have no polarity here. This is tough. But we know the net charge is what? Yeah, net charge is neutral. It's a neutral molecule. And the electrons spread out through here should hopefully look like just what I drew with the p orbitals, and I drew it up. We drew it up top too, right? That is, you do have some more than single bond between here. You've got a little bit of pi bonding in there. We will build on this. We will repeat these same things over and over. Okay.
This is the same as the top two structures, so the resonance area. It's not like a final answer, it's just another structure, right?
It's the same as the top 2 structures?
Like,
No,
we draw
well, this structure is close to this, it just doesn't have the methyl on the end.
the two structures that we already drew. So is the third structure, is that, like, do we draw a resonance arrow and then that, or is that our final answer? You know what I mean?
What do you mean, you want to draw another one?
So-
No, I think it's the major resonance structure. Predicting the major resonance structure.
Major is this one,
Oh.
because there's no charges. I'm not sure what your answer is.
Is that just another resonance structure? Not a dipolar resonance?
Which one?
The Orm bottom.
No, this is the hybrid.
Oh, the hybrid.
This is the culminated, the mixture of all your resonance structures. Look, okay? The resonance hybrid. Whenever you start doing resonance, your resonance structures are fake. The true structure looks something like this, but the true structure is hard to draw. Now I've got more than 2 resonance structures, but if I only had 2, I could have said one's red and one's white. And if we combine red and white, what's the true structure going to look like? Pink. But pink is hard to draw. But red and white are easier to draw. This gets a little vague. But it's actually the true structure because the electrons are really smeared out in there. Now, I combine more than just red and white. I combine red and white and some third thing. So what is that going to look like? Well, we tried to go through and we came up with this. We'll do more of those. I decided to be nice and gave you, on the front of the back page, the golden rules of resonance. Front of the back page.
golden rules of residence. Summary of some of the more important rules. I don't always give you guys this, but I decided I'd give it to you. Thank you. You will see rules there. For example, all resonant structures have the same net charge. Net charge of this is neutral. What's the net charge of this? Neutral. If all of a sudden you've got a neutral end and this one's a positive, you've got something wrong. You can't have different charge. You're drawing, it's the same compound. You're just drawing different representations of the same compound. It can't go from neutral to charge. Okay, there's some limitations to that example, as I tried to explain, but I know when you're beginning, you don't quite understand the rationale until it sinks in. All right, let's keep at it. Comment on resonance hybrids. Well, we just did the resonance hybrid. True structure, partial charges. I didn't show any partial charges. True bond lengths. Again, this stuff is easier with examples below. I didn't say bond order. Bond order is basically number of bonds. Okay? Bond order between these two carbons is 2, double bond. The bond order between these two carbons is 1, single bond. What's the bond order between carbons 2 and 3? Approximately. 1.5. That's just bond order. And basically, we've already been saying that, right? That's called bond order. Now, is it exactly 1.5? No, like I told you, we just sort of said, okay, if it's in between, we're going to call it 1.5. Actually, if you look at your blends, it's actually going to be closer to 1. But it's more than 1. Resonance stabilization of cations. Question.
So whenever we have a question on like that on the test, do you want us to do more than 1 or 1.5?
It'll depend on the details of the question.
Okay.
Let's look at some more. These will be, let's look at cations. These will be a little bit more intuitive because dealing with the charge is just, let's look at it. Okay. Cations can be stabilized by resonance. We did a couple of examples of this with our alkene chemistry. And we saw that resonance was actually better than being like tertiary. Okay. Well, let's look at that. We can stabilize cations using a pi bond. By the way, I didn't do something up here. I think I'll do it, go back and do it now. Okay, those resonance structures, we drew them by using our arrows, mechanism arrows. And we're going to move electrons here, and then move electrons here, or whatnot. You could have did it another way. Now, I don't recommend this way. It's actually a very bad way, okay? But this is essentially what we were doing. That is, first off, how many p orbitals in the compound there? Okay, I almost drew them all. Yeah, there's 4, right? 4 p orbitals. How many pi electrons in the system? 4. Okay. There are your 4 p orbitals. Put the 4 electrons in those orbitals any way you want. And each time you put the 4 in there, draw the Lewis structure with that. And you'll be drawing resonance structures. Yes. I could put 1 in each. If I put 1 in each, which structure do I have of the 3 I drew? Well, 2 of them I drew. 1 was already there. Which one is this? That is like this. 1 electron makes pi bond, 1 electron makes pi bond.
It's the one that's there.
The original, right? Okay. What if I put 2 here, one there and one there. That would actually be the second one. Because I got pi bond, nothing here, so that's like a cation. 2 here, so that's like an anion. Okay. What if I put 2 there, 1 here, and none here? Well, that looks like a pi bond. Looks like a lone pair, and then there's nothing there. What was that one?
That's the third one.
That's the third one. Okay. Could you put them in any other ways? Yes. I could put, what if I put 2 there, leave that empty and leave that empty? Well, that would be negative, negative, plus, and plus. I could have drawn that resonance structure. Every different way you could put them in would be a difference. Those would all be resonance. It's just different ways of putting your electrons into your system. What would be the best way to put them in? The first way. That's really what's going on here. You have a system of 4 electrons, and the electrons are all spread out there. Okay, but I don't recommend this way. It's better to do it systematically using your mechanism arrows and go from one to another. Okay, for example, let's draw a resonance structure of this cation. Very importantly, how do you stabilize a cation? Do you move electrons towards it, or do you pull electrons away?
Towards it.
Towards it. That hopefully should make sense. What electrons can we move toward this in a way that we've already done today? Windshield wiper. Can you see this? Move these over. Make bond there. What does that give?
Another
It gets double bond here and cation there. Okay. And here, that's the only other resonance structure. Now, it's theoretically not. I could draw a resonance structure where I do that, but now I'm creating more charge. The goal here is not to draw all possible resonance structures. The goal here is to stabilize the cation by resonance. And there's only one where you stabilize the cation by resonance. So if I tell you these are the 2, which one is actually correct?
It's the same thing, right?
You could say both or neither. Neither is correct. What's the true structure of this cation now? The true structure is this. What's the bond order between carbons 1 and 2? It's actually 1.5 because look, single here, double there. And what's in between? 1.5. What about between carbons 2 and 3? Double and single, what's in between? 1.5. Charge, much easier to do here. Positive here, neutral here, what's in between? Partial positive. Neutral here, positive here, what's in between? Partial positive. If you could look at this cation, it would look like that. That is, the charge isn't just right here on this end. It's actually delocalized onto the other carbon, other end as well. We see that in our hybrid. If you could take a picture of the compound and charge intensity was illustrated with color, like often in books, you have the same color here, same amount of charge. Charge, we said, has been delocalized by resonance. And so it's a very stabilizing effect because the charge is not just sitting on the carbon. It's really not a full plus. This carbon is really only a partial plus. There's your resonance hybrid. The bond order. Okay, question. Which one of these resonance structures is better? Or major?
I do the same.
Which one's a major contributor? Correct. They're the same. equal contributors to the hybrid. In this case, the hybrid is a perfect blend of the two. Perfect blend. Down below, resonance is often seen with benzene compounds, aromatics. They have pi bonds, and multiple pi bonds. You can show 3 additional resonance structures of this cation. Can you show all 3 of them? First step, how do you stabilize a cation? Move electrons towards it. What systematic method do you know to move electrons towards it? Well, here's the scientific term that I use, windshield wiper. And do it one at a time. Right. Okay, got the pi bond here. Move it over here. Either one can be considered a pi bond. I mean, one is connected, the other one's just laying in there, but either one's considered a pi bond, whatever side you're on. Now we have over here, boom, boom, plus here, correct? So we're starting to delocalize the positive charge by resonance. But we can keep going. So these can windshield wiper up. Pull them up. Resonance arrow. Double-headed arrow is a resonance arrow. It means you're going in between resonance structures. Okay? You don't use equilibrium arrows. These are not in equilibrium. We're just showing different representations of the same compound. The paper you have in front of you is pink. Is it in equilibrium between red and white? Is it just bouncing back and forth between red and white? No, it's just pink. What we have here is, I'm just not able to show you pink, so I'm showing you red and white. That doesn't mean that there's two different things. The true structure is pink. These are not different things. This is one thing we're drawing, just different representation of it called resonance structures. So we use resonance arrows. They're not in equilibrium. Resonance is actually a bad term to some degree because it sounds like it's resonating back and forth. It's not. Move those up. Everything, it's like we're doing mechanisms, but with, okay, what does this arrow mean to you? Move up. So now it's up here, yeah? We didn't do anything to the rest. And what's here? Positive. And then we can do one more. These can move over, yeah? What if we pull these down? What would that give?
Give us
Pretty much, except the pi bonds would be moved around in the ring. Okay? That would be theoretically a different resonance structure. But the cation, if you focus on delocalization, the cation would be back to the same position. Okay, what does the true structure look like? What does the resonance hybrid look like? That's what we're asking here.
So ring with dashes all throughout the ring. and not-
Also here.
Yeah.
What type of charge is on this carbon? Full plus?
Partial positive.
Partial positive. You see? It's no charge when we start delocalizing the electrons.
In the whole ring.
To a degree, mainly on these three carbons here. But look at your resonance structures. Positive follows that carbon, and this carbon. You can see the compound, it would look like this. Is one of those major?
What makes it major?
Major? Most stable? Best? Call that the major contributor. That is like a child, a baby.
They all have the same charge.
If the baby looks more like mom, then we say mom was the major contributor in making this baby, the appearance of this baby. If the child looks more like dad, then we would say dad was the major contributor in the appearance of the baby. If it looks a perfect blend of mom and dad, we say they were equal contributors. That's what we're doing here. Okay. That is, should the baby look more like one of those? Now see, you say, should the baby look more like mom because she's prettier? Then the answer could always be yes. And for chemistry, then yes. It would always look like this one because it's more stable.
If you brought the last one down, wouldn't it put the charge on a tertiary carbon as opposed to the very first
Tell me,
one?
where?
On the far end?
Here?
Yes, sir.
Bring it down, that would be secondary.
It wouldn't be on the top.
No, how would you get it here? When you windshield wiper, how did you end up with charge here?
When you go down, doesn't it go? Oh, okay. I
No,
see.
if you pull this down, you make pi bond here and you leave that.
Yes, sir.
Good. They're all secondary. This one's actually best because we keep the benzene ring. The benzene ring is very magical. It's maintained. It's a miscellaneous thing. Otherwise, they're pretty darn similar. Going forward, we'll see some that are definitely. That is, the benzene ring kind of wants to be sort of a nice thing there. And so if this one is favored, that means even though we acted like these were all equal charges, where's there actually more partial plus? Well, you look at your major structure. If this one contributes more, then that means there's going to be more plus here. That's hard to show that because I'm only doing partial plus. But there's more partial plus here than the rest because I identified this as being the major contributor.
Doesn't that also have to do with that being the benzoic position and that positive charge would be more stable there?
Well, the positive charge is stable here compared to there
Right.
because of resonance, because of the whole thing. This is why the benzoic cation is stable. We haven't called it that yet. It's called a benzoic cation. It's typically, maybe mentioned here, definitely in organic too. The benzoic cation is very stable because it's resonance stabilized. Okay? Compare that to, what if we had the cation here? Now, 2 weeks ago, you would have said, that's secondary, this is primary. That's better. that turns out to be only a minor consideration. That's better because hugely why? Resonance. Can you draw a resonance structure of this? How are you going to do it? You're going to windshield wiper has no resonance. That's an isolated cation that charges fully on that one carbon and it's primary. Not only is it secondary, but it's been delocalized by resonance. You can't do your windshield wiper, but also here's the other reason. If you call that sp2 with an empty p orbital, okay, empty p orbital, that's why it's a positive. Is there a p orbital here? No. So you can't do resonance. Ultimately, when we do resonance, we first have the pi system. The pi system here is there. Look. They're all lined up, and the electrons are all spread out through here. There's no p orbital. There's no resonance. That's not participating in any resonance. And so it's not delocalized, and it's not as good as the benzylic. Okay, that was A. Here's B. Stabilization by a lone pair. Now instead of windshield wiper, we're going to do something more like we did on day one. And we've also done a couple of times since. Got this cation. How can we stabilize it and delocalize it? We've got a lone pair next door. And we can ask these electrons, hey, oxygen, next door carbon needs electrons. Can you move in and make bond? What does that give? Double bond. One lone pair left on oxygen, and that is a plus charge on oxygen. It's an alternative Lewis structure where all removed is pi electrons. There's a resonance structure. Okay, how would you localize the charge? Charge has been moved from carbon to oxygen by resonance. Okay. Let me ask you this. I could ask you this before we started. What's the hybridization of that oxygen? You gotta be careful. Whenever you do resonance, you can't say the first one's something and the next one's something else because it's the same compound. Resonance is one compound. So it can't change. The answer can't change.
What's SP2?
SP3?
SP2.
SP2. Why is it SP2?
Because of the resonance.
Because anytime a lone pair is next to a p orbital. Yes. What's hybridization of this guy? How many H's? One H? Not two. There's two, it would be neutral. It's positive because one H. So sp2 with an empty p orbital. Yes. Okay? Let's redraw it so you can redraw it on your paper. Boom, boom. sp2 with an empty p orbital. It's empty. I can just draw like that. Okay? Is one of these lone pairs going to want to be in a p orbital? One next door.
Yeah.
Did we say that? So we put one of these in a p orbital, and the other one is in the trigonal planar. Now why would this one be in a p orbital? Now what's going on here? Now we can put the electrons in any way you want. We can put two here and leave that one empty, and that's what you got here. Or we could put one here and one here, and have some pi bonding, and that's what you got there. And to get to that, we can say this. We've got a lone pair here in a p orbital. It's going to interact with this p orbital And at this point, you have two p orbitals interacting, and there's two electrons there. This becomes one system. The two electrons are now in here. It's kind of like that. Okay. What you got here when you got resonant? Okay, which one's major? Which one's minor? Is there a major one here? Or are they equal?
Because you want the positive charge on these electronegative atoms.
So you say which one's major? Major?
Yes,
Does anybody have another answer?
I'd say the right one,
This one's actually major here.
because the oxygen can handle the charge more than
I was actually major there. This one's minor. Okay. Before we do that, well, let's look at the hybrid. The hybrid would look like, what type of bonding is between the O and the carbon? Single or double? 1.5. What type of charge is on oxygen? And here, see, there's your true structure. Why is it just not this? Why didn't I just say the true structure is this? That is, instead of a full double bond, it's only a partial double bond. Why? Because oxygen is not just going to just give these electrons up, it's still going to pull. And so some of the electrons are more back to oxygen. But it hasn't pulled back completely. There's a small amount of bonding interaction there. And so there's a small amount in between here. So you get delocalized, vague bonding that's really there. Why do I call this one's major?
oxygen can handle the charge more.
Here's the reason, more bonds. You agree it's got more bonds than that one? What's negative? What makes this one look bad? Yes, positive on a more electronegative atom kind of looks bad. But more bonds trumps that. And here's the take-home. Oxygen, these electronegative atoms, oxygen, nitrogen, chlorine, etc., don't mind being positive as long as they have an octet. Does that oxygen have an octet here? 2, 4, 6, 8. Yes. It has an octet, it doesn't mind being positive. What you don't want to ever do is show an oxygen or fluorine or something like that with a positive and no octet. If you do that to an oxygen, it will be very mad at you. That's one of the entries on the Golden Rules of Resonance page. More bonds. We can also do this. All atoms have octet. Yes. Carbon has octet now. Everything has octet. Over here, carbon doesn't have an octet. So the hybrid looks more like which one? Actually looks more like this. So it's actually more positive on the oxygen than carbon. Even though that's a little counterintuitive. Okay. Show all possible resonance structures of this that involve the localization of the cation. While you're working on those, I'll pass back the SciFinder assignment. Please yell loud enough so I can hear you. The B2 lab first. Thomas Stringer.
Here.
Remy. Taylor. Jake. Catherine. Alexandra.
Here.
Karina.
Here.
Matthew. Victoria.
Here.
Kayla.
Here.
Jennifer.
Here.
Tussin. Bianca.
Here.
Julia.
Here.
Jacqueline.
Here.
Lauren.
Here.
Nick.
Here.
Megan.
Here.
Esther.
Here.
Shireen.
Here.
Rosalind.
Here.
Anthea. Kimberly.
Yes.
Charlotte.
Here.
Kate.
Here.
Jonathan. So guys, the top compound, number 1, you're making in lab today and tomorrow. One of the assignments for that is to find a SciFinder or a literature bowling point. Well, you've already done that. You've done that here. Please make sure you read directions. One of them was supposed to be under vacuum, etc. It was supposed to be correct format for references. That's included in the guidelines to reports, etc., in the lab manual. I ended up not checking if the journal was available in the AU library. That's an important thing to know. I saw some that I disagree with your answer on that. But one variable there was maybe we have multiple years, but we didn't have that particular year. That becomes a little bit more difficult for me to check 50 times. So I didn't realize that could be a variable in your answer. I need to better define the instructions. This is the first time I've ever done this sheet. At the bottom, there was only a melting point available for compound 1. There was none available for compound 2 and 3. Some of you had. I don't know where you got your melting points from. If anything I marked X and you disagree with, please let me know. I mean, I'd like to know where you found the melting point for compound 3. For compound 2, there was a chem abstracts number available, but there was no melting point available, and thus no reference. Only compound 1 had everything available. SciFinder gives predicted values. I didn't ask for predicted values. I asked for literature values, real values. Predicted, I've never used that. It doesn't seem to be of use. If you have any questions about what I marked wrong, please ask. If you can convince me that what you have is right, then I will give you credit. Okay. Questions about lab today and tomorrow? Group lab, doing hydration of an alkyne to make 2-hexanone, which is a top compound. Questions about lab?
Are we
Yes.
meeting here or? Sorry.
Yes, we'll meet down here.
Okay.
Just about every lab will meet down here.
Is our, like, report that we turn in at the end, is that done as a group too?
Yes, that's a group report. One report. one group performing the reaction, and then that group writes one report. Corrections are in the left handout. Other questions?
You took a lot from last Thursday's group this Thursday.
Yes, the bromination lab, yeah, will be due Wednesday, Thursday. Wednesday or Thursday, depending on when you come to lab.
Will the 3 o'clock also do the following lab?
No, I'm not going to have them do both the same day. It will most likely be due Monday, Tuesday. Okay. We have a long pair here. These electrons can move in, and we can get that there, yep. Could we draw another resonance structure here?
Yes.
What do you have?
Maybe,
A pi bond could windshield wiper in. 2 lone pairs and pi bonds. Yeah. Now, the other one comes from this here in terms of my movement. So I'm going to come, I can maybe come down like this. And I'm going to call this A. And so that's the A pathway. Now we can windshield wiper over. I'm going to call this the B. And this leads to boom, boom, boom. Here, here. There's 2 resonance structures. In both cases, the charge has been delocalized, either onto nitrogen or to another carbon. Of the 3 on the board, which one would you call major? The major contributor to the hybrid. This one here, major. Why?
More
no
bonds.
charge on the nitrogen.
More bonds.
More bonds.
Yes, it is, but that's not related. That's actually kind of the bad part about it. More bonds. And everything has octet, referred to the previous one. That is, the hybrid is going to look more like that. That is, in the hybrid, there's which atom has more of the plus? You drew the hybrid. If you could look at the blend, which atom has more of the plus? The nitrogen. Because the hybrid is going to look more like this one. So it'll have more of the plus. Nitrogen will have more of the plus. There you go.
Would the minor be the primary cation?
Yeah, but this is also technically primary. Because it's only bonding to one carbon.
Yeah, but it's closer to the nitrogen, so.
Yeah, what's that going to do for it? That's just going to allow you to draw this one. So, yes, this does look like primary, but that's also primary. So, I don't know if I'd ask you which one's minor. Cause
It could be 2 of them could be equal.
yeah. Now, if this one had maybe like a methyl on it, and that one was secondary, and this one was primary, then I would probably say, yeah, I think this one is better. But they're both they're both technically primary carbocations. Bonded to one carbon, bonded to one carbon. So it's kind of tough. But that's clearly the major. Okay. Systematic approach to drawing resonance structures. All right, we've seen an example like this before. Remember, we went back and looked at it. Resonance can influence the regiochemistry of your reaction. For example, you do this alkene reaction up here with HBr, which product do you predict you'll get, left or right? Well, the question is really which cation is going to form.
Right.
Are we going to form cation on top or bottom? Now,
Doesn't
that
matter.
one's strictly a secondary cation, that is strictly primary.
Bottom.
But it's actually going to be the bottom.
Resonant.
Because this is attacked this way. UH here. Cation there. Well, that's the bottom. What would the top look like? Cation there and UH here. Okay? When I say top or bottom, this is what we're looking at. Cation on top or bottom. Which cation is more stable?
The top one,
Why?
the resonance between them.
Because we can do resonance. Double bond there, new H is up there, methyl, and there. Resonance. Do you have any resonance here? No. No p orbital, no p orbital. It's an isolated cation. That's a delocalized cation. That's better. You're going to get cation down here, and the Br minus attacks there. Or we could bring it in here and attack here and move these back over. You can always work with any resonance structure. So, that's the one you're going to get. Yeah? How about below? HI. Which product we're going to get? Would you rather make cation on left or right? They'll both be secondary, but is there anything else going on? Cation here would be a benzoylic cation. We can do that resonance. Cation here is much better than there. We're going to get this product here. Question?
What did you say about the cation there? It was what?
A benzoyl.
Benzoylic, more stable. That's just like what we looked at on the other page when we did the resonance structures of the benzene. If the cation's there, we can draw resonance structures and put the charge all throughout the ring, or here, here, and here. If the cation is there, you cannot. It would be isolated. Right? If the new H is there, the cation's there. That is, if we put charge on the right, can you do any resonance of that? No. But if the cation was here, you'd be able to do lots of resonance. Okay, resonance stabilization of anions. How do you stabilize an anion? Do you move electrons towards it or away from it? Away. Away. That's the starting point. So here's an anion, a carbanion. Can you show resonance structure? Well, here's what you don't want to do. Pi bond. Boom. Well, why would you move electrons towards an anion? Right? That's no good. And then I'll see a product like this, or a resonance structure like that. And then I'll say, well, how many H's are on the end here? 2. Still 2 there, so you're showing 2, 4, 6, 8, 10 electrons around carbon. I mean, you're starting to break so many rules. The first one was, how do you stabilize an anion? If you don't move electrons towards it, you need to move electrons away. These electrons need to go somewhere. Okay, this is a new on-the-board technique. I call this in-out. These electrons are going to move in, but this carbon can't make 5 bonds, so we got to move something out. So let's move these here. What does the arrow movement give? Can you show it?
Well, here.
Electrons moving in to make pi bond between these. This pi bond, the electrons are moving out onto carbon. Pi bond consists of 2 electrons. We're moving those 2 just both onto carbon. And so that's going to give boom, boom. We now have that and that. have delocalized the minus charge from one carbon to another. Okay, which one's major? Which one's minor? They're the same. This is where the child looks exactly like both mom and dad. Perfect blend. That is, what's the bond order between carbons 1 and 2? Double or single? 1.5. How about between the other two carbons? What's the charge on this end?
Partial negative.
See, if you could look at the child, it would look like that over there. This is called pi bonding, delocalized bonding. These are actually fake. Because the molecule doesn't have just a lone pair here and just a plain pi bond there. No. Or here. This is some bonding here. And okay? Hopefully you're starting to get... So what's the bond order between 1 and 2? 1.5. Also between 2 and 3, 1.5. Which carbon-carbon bond, which carbon-carbon interatomic distance is longer? The 1,2 or the 2,3? Well, isn't a pi bond shorter? Isn't a double bond going to be shorter than a single? Yeah, but this is a fake structure. This is not really correct. The true structure is this. You've got the same amount of pi bonding here as here. Bond length comes from bond order. If they have the same bond orders, they're going to have the same bond length. Yes? Both of these bond lengths here are the same if you could look at the true molecule. This is some of the same stuff I tried to discuss on page 1, but it's easier to discuss here with these charge guys because you can see differences a little easier than with the all neutral. What about this? This is the anion of phenol called phenoxide. It's more stable than a regular O anion. Why? Resonance. Can you draw resonance structures of this? It's an anion. How do you symbolize anions? Move electrons away. I recommend the old in and out approach.
When you say in and out, like, is that for one step? Like, would you move one pair of electrons and then one out on the same?
Yeah, like we did up here. We moved these in. You can't show the result of that. You'd have 5 bonds here.
Okay.
So we've got to move those out at the same time. This is just us on the board. This is not a chemical phenomenon. This is our approach for doing it on our paper or board. The windshield wiper. That actually never happens in chemistry life because as soon as the cation is formed, it's the hybrid. It doesn't form and then the electrons move over. We're only doing that on the board. As soon as it's formed, it's the hybrid. These exist as hybrids, and that's it. These electrons can move in, and this pi bond would have to move out. And we get
See that stuff across here.
No. I gotta think about what I'm doing. I was, thinking about two other things at the same time. Yes, one lone pair moves in, two lone pairs left. Lo and behold, that's a neutral oxygen, 2 bonds, 2 lone pairs. And what did I have up there at first? It had minus, minus? Well, all resonance structures have same net charge. If that's minus, how is that all of a sudden 2 minus?
Wrong.
It's wrong. Okay, we can just keep going. These electrons can move in here, and I'm using the outside. I mean, it looks like that's the pi bond, but it's the same. And move this pi bond here, make pi bond here, and move the pi bond as a lone pair out here, yeah? Pi bond here, move this pi bond here as a lone pair. That's going to be a minus. And then we keep going. Sometimes these don't exactly come together, right? Move these down here and move this pi bond out onto that carbon. That carbon minus. What if I move these here? What do we move out?
You end up with the same structure that you started.
Okay, well hopefully you see you have to move the pi bond out, because if I move this, you can't move sigma electrons. That's one of the golden rules. Probably one of the rule of two. When you do resonance, you only move pi electrons. If you move sigma electrons, you're going to be breaking bonds. Everything has the same connectivity in all your resonance structures. No. Pi bond is what moves out. And yes, that's going to give you back here, the charge is going to be back on oxygen. Okay? That's the phenol anion. What if we just had, what if it was just cyclohexane here instead of all these pi bonds? Can you do any resonance here? No, there's no p orbital here. I mean, what would you do? Move these in and you got an H here. I mean, what are you going to do? Just make 5 bonds to carbon? There's no pi electrons to move. There's no p orbital there. I mean, since there's no p orbital there, the oxygen's actually just plain old sp3. There's no reason for any long pair to even be in a p orbital. Which one's more stable? That one, because you delocalize the charge. Thus, which OH compound is more acidic? Don't mess your notes up. Just which alcohol is more acidic? Whenever we did acid base, we said, okay, which is more acidic? Well, let's consider the anions. Well, here are your anions. Which one's more stable? This one. That means the OH compound is more acidic. Indeed, phenol has a pK of about 10, alcohol's about 16. Phenol is much more acidic because the anion is delocalized. All right, resonance. Okay. Resonance in neutral molecules containing heteroatoms. At the very beginning, it was neutral with just all carbons. Harder to deal with. But heteroatoms is a little bit easier to deal with because it's more intuitive.
Which one is major?
The phenols,
Yeah.
which one do you think? Good question. I see a clear winner there. And over the anion, first off, they all have the same number of bonds, if you look at that. Okay? So it's got to be something else. Which one's, why the first one?
It's the oxygen.
Anion, you'd rather have anion on oxygen than carbon. What's another reason the first one is better? The benzene ring is intact and it sort of just gets to be an isolated benzene ring. But anion on oxygen,
Thank you.
all of them have the same number of bonds. All atoms have octets in every structure. So you got to find the difference. Okay. Show resonance structures of this guy. No charge, so you're not kind of focusing on any charge. But do focus on the lone pair, okay? Using lone pairs. First off, a week ago, at least 10 days ago, what type of orbital is this lone pair in? P orbital. Now, when you came into the class, would you have said that was a P orbital? You would have said no, sp3. Why does a lone pair want to be in a P orbital if it can?
Because there's one next door.
And that's called resonance. Yes. Yeah. These lone pairs that are in P orbitals are great places to start with your resonance. This is actually just like what we did. Previously we had an O of a lone pair out there that we used. Now the O happened to have a negative charge. So what? That doesn't mean you don't have to have negatives to do resonance. You can do resonance of neutrals. So this is oxygen, this is nitrogen instead, but it's got a lone pair. I'm telling you right here, the lone pair, if it's in a P orbital, is a great place to start for doing your resonance on the board. Okay, here we go. Hey, lone pair in the P orbital, great place to start. I'm going to start right there. These electrons, you can almost act like an anion. The electrons can be used to, okay, electrons in and move these out. What does that give? We'll bond to N, two H's, and we move, what's now on this carbon? Okay. Oh, we got charge? Yes, indeed, that's a negative because there's also an H there. Okay, this is a net neutral molecule. That's got to be net neutral. So if you got a negative, where's the positive? Yeah, the nitrogen's positive. And also have pi bonds here and here, right? This lone pair is in a P orbital. We can go back to the very fundamental. I don't know if you want to draw this because you don't really need to. What do we have here? We got P orbitals all the way around, right? 1, 1, 1, 1, 1, 1, pi bond, pi bond, pi bond, pi bond. But of course, there's also bonding in between there and there and there. Then you got this nitrogen over here. We could make that trigonal tetrahedral and with no P orbital. Or we could put the lone pair in a P orbital. And if we do that, now it gets to interact with all those P orbitals. That's actually a better scenario. And that's why we said 2 weeks ago that the lone pair is going to want to be in a P orbital. Now this becomes starting to look like the hybrid, but it's cumbersome. Let's do individual fake structures and arrive at the hybrid that way. We call these resonant structures. These electrons can move here. These electrons can move out. and you can draw one more. So, is this lone pair sitting right there on that nitrogen? Or is it delocalized onto other atoms?
It's delocalized bonds.
Yeah. So is that lone pair going to be highly reactive as like a base? No, it's less reactive. We said if a lone pair is in a pure orbital, it's not going to be basic. Why? Because the electrons are delocalized. Let me ask you this. If we drew the hybrid, what would be the partial charge on the nitrogen? Partial plus. You see that from your resonance structures. Okay. If it's partial plus, how attracted is it going to be to proton? Not very. This is all just the same explanation of it's not as basic. It's actually got some partial plus chemistry. I erased it before we answered the question below. Which carbons of the benzene ring of aniline are most electron rich? That is, if we drew the hybrid, I didn't draw the third resonance structure, but the hybrid would look like what? It would actually look like this. Partial plus there. We drew two resonance structures. One was minus here, the other one was here. The third one will be here. And here's your answer. Which carbons of the ring are more electron rich? That one, and that one. They're partial minus. These are neutral. Such an answer comes from assessing your resonance structure and the hybrid. Okay, try this one on your own. Which amino group of the two compounds above is the most electron rich? Here we've got an extra group on the benzene ring. So you may be able to draw these into here, but then can you keep going and move the electrons into this group? In one case you can, in the other case you cannot. Draw all resonance structures and then assess them and answer this question. Let's finish up here. Please look at this and we'll see if you have any questions about this bottom on first thing Wednesday. There should be resonance in the workbook. What else is here? The golden rules. I usually put resonance on golden paper because of the golden rules. Golden rules of resonance. Please read. It covers about everything there. So that's the summary page. And then a little analogy on the back. Benzene is neither Charlie Brown or Dennis the Menace. Somewhere in between. Somewhere in between. Question? Okay, guys, see some of you this afternoon right here.